so nice to stand in front of people again, actually. It's like, are you real? Do any of you work for optics and design? So, thank you. My name is Hausmann. I'd like to talk to you a little bit about user interfaces and Rust and Slint on microcontrollers. I am a software engineer. I've spent my majority of my time as a software engineer writing C++ code, and about 2 years ago I changed over to write Rust code. Ever liked it since then, and I co-founded a little company together with my colleague Olivier called 60FPS GmbH. We are in total 4 people. There's one more dude in the back there, Tobias, and we also have an intern. Every company has to have an intern. He's remote. And we're a small startup here in Berlin, and we are creating a UI toolkit called Slint. We're doing this entirely in Rust. We love it. We love being part of this ecosystem, so we're also happy to be part of the Rust Foundation. So, brief agenda. I want to give a quick perspective on what microcontrollers are, sort of what their relation is in the overall landscape of computing. I'd like to show you a little bit about what Slint is, and then how it looks like on a microcontroller. So what's the deal with microcontrollers? A quick perspective on modular hardware. I mean, I started programming with an IBM PC, and that was like a box I could open. I could put cards in and out, and that was really cool. Actually, this is what made programming and computing very accessible. And today, that's sort of a gaming rig, right? It's one of those things here. They're very expensive, thousands of euros. They're quite literally heavy, but they have practically unlimited RAM and unlimited disk storage, and they also have a kind of unlimited energy consumption, several hundreds of watts. You go down there and you have an embedded device. This is what you have in your hand, or what people have at home often. These are much cheaper. You can hold it in your hand. They're still very powerful. They still have gigabytes of RAM, and you can attach SSDs to it, but they take 1 order of magnitude less of energy. So everything is going down an order of magnitude really here. They can still run Linux. This is very cool though. But I'm here to talk about microcontrollers, and that's another order of magnitude cheaper, smaller. We're talking about something like this thing costs a couple of euros, 2, 3, 4, 5 euros, something in that range. It has only hundreds kilobytes of RAM. That's kind of little. This thing has, I think, a megabyte of flash. You can get it on a board with up to 16, but that's about it. But it takes almost no energy. You can run it literally on a battery. I think Olivier has one with him with a battery connection. You can see it afterwards. You can run it on a solar panel. This is actually really cool. You can put these things anywhere as long as there's like a glimpse of sunlight somewhere. Unfortunately, it doesn't run Linux, so that makes the programming a little bit more nitty-gritty. Fortunately, the nitty-gritty is made easy with Rust, as always. There's an absolutely amazing ecosystem of different crates and also documentation and tooling around these little things, from crates supporting different boards, different peripherals that you connect these things, different kind of screens, etc. And Rust itself, the core tool chain is also very supportive towards this entire ecosystem and developing for microcontrollers by supporting all sorts of configurations, like building without a standard library or building only those parts that you need. And I also like to shout out to the Knurling project. That's, I think, run from here, from Berlin, from Ferro Systems, which is absolutely amazing. It has amazing tooling when you program these little things, how to access them, how to flash them, how to get log output. There's no, there's no other way of, seeing what's going on there sometimes. So the ecosystem there is absolutely amazing, and I highly recommend if you ever dig into this thing, don't start with those C SDKs that you get with those devices. Go straight to Rust and use whatever is there. It's really, really good. So, short pause for this. We'll get back to them in a moment. I want to talk a bit about what Slint is, so you have an idea of what the context. We're a UI toolkit. Our basic philosophy is that we want to provide a fresh, new approach to creating user interfaces on devices and laptops and the like. The basic principle is that we want to enable rapid design. We have a design language that we use, and it is strongly typed. So it's not like JavaScript, but it's more closer to Rust in that sense. It's strongly typed. It tells you when there are mistakes, when you make accidental mistakes, when makes them intentionally. We have an IDE integration, a Visual Studio Code plugin, but also an LSP that works everywhere else. We have code completion and these kind of things. And we have a live preview, and that's really cool. And you'll see that. And all of this is supposed to enable the developer or a designer to iterate quickly on getting the design that their boss asked them to implement. We're also cross-platform. That's a bit in our DNA from our former careers. We've been doing cross-platform software forever. So naturally for us, we had to do this on Linux, Windows, Mac OS. And thanks to also Rust's awesome Beinchen and the overall ecosystem, we also run it in a web browser, and that's also great fun. It's great for demonstration purposes. We don't really have anything architecturally specific in our toolkit, so it runs on any architecture you throw Rust at, or Rust throws itself at. We have support for GPU acceleration, which you have to have on those embedded devices, of course, and we also do software rendering. This thing doesn't have a GPU, so we need to do everything by hand, basically. One thing that makes us a little special is that we are multi-language. So we implemented our toolkit itself purely in Rust. That was a natural choice for us. And we also have, of course, crates that provide the Rust-based API, and we maintain those crates, happy about that. But we provide also an API for C++, and we provide an API for JavaScript, and we've designed it from the ground so that it can be used for multiple programming languages. We've been doing APIs for other developers, again, the vast majority of our careers at least. So this is something that's really to the heart of us, and so we spend a lot of time trying to design idiomatic APIs in Rust, but also in C++ and JavaScript and the like. These design files, we compile them to native code, so we can create something very efficient and also small so that it can run on these things again, and fast. And we also have a dynamic interpreter to run inside of JavaScript. And this is also what we use for the live preview. All right, it's demo time. For that, wait, I want to show you briefly the setup today, right? So the setup, you see it on the screen here, but also here, this is the Raspberry Pico. That's got this little black dot on it. It's a dual-core RP2040 MCU running at a mere 133 megahertz. It's got only 264 kilobytes of RAM. It's got an LED somewhere on it. It's got a button, and that's about it. And it's got plenty of pins, and you can do anything with those pins. So this thing was not, of course, not enough for it. We had to attach a screen to it. So we bought a little waveshare screen, a 2.5-inch, 320 times 240, I think. It's got a resistive touch. That's not so great, but it works. And the magic happens when you connect these two. And then you have a little device that runs by itself. Here's a micro USB, and you can or put a battery in it, and then this thing is a computer with a touchscreen attached to it. And as I said, this is bare metal, so there's no operating system. We have to do everything by hand. This is the core setup. Let me show you how it looks like, actually. Yep, camera. Because that's the trick, because if I show this up, it won't be visible for you in the back, and then it won't be in the recording. So I've got a little camera here. And then I'm going to connect it. I already flashed something in it, so you can see first how this looks like. Where am I? Yep, here we are. Let there be power. Did I bring the wrong cable? No. There we go. So, oops, can you see this? Yeah, this is the boot time. So it comes up relatively quickly. There's some garbage on the screen. That's sort of in the nature of it. And this is what we call our little printer demo running. Oh, this is, it's better on the big screen than I see it. This is supposed to be a little printer, and it's interactive, so you can tap on it, and then you can scroll in it. We have a night mode, or dark mode as it is called, right? Come on, there we go. It also fits the ambient light here a bit better. Yeah, this is our little demo There's an ink measurement animation. We have this demo running on a bigger screen, and we ported it into the Pico and made it a bit smaller. So this is what we call a printer demo. So how do we do this? Now I changed to exit the presentation mode. Where's my Visual Studio Code? Here we are. So we've got a Visual Studio Code plugin, and what I've loaded, and that usually would be a Rust project. So here you can see some Rust code. And this is where the business logic of a printer is. You will find things where you can probably guess what it is, like there's a pop-up. No, there's like a callback, a printer queue, and there's a function called onStartJob, and then you see that must be some kind of callback, and that's indeed when I press on print, that function will be called, and this is where I could send something to a real printer that was connected to it or so. This is the business logic part of it, but the design is separate in a separate file, I said. And this is a .slint file, and we have a preview. I can show you how that looks like. There we go. Let me make this a bit smaller. So you can see this is the whole design also separate, and the whole design is capturing everything here that is related to the look. So everything you see here, this is dummy data, mock data that is inside, but all of this is also just viewable using a live preview. So this is not running. This is not running on the device, but I can do the entire design on the desktop, and this is quite neat. This is live actually. So suppose my boss calls and says this printer is good, but for the German market, we have to do a fax support because everybody in Germany uses faxes, right? So the scanner has to go away. We have to do a fax. So I can just edit the file here, and it's edited right away in the live preview. And then I can say, oh, the color, the yellow is good, but today this is a bit of a purple environment. So there's an action button that represents those buttons there. I can see there's a border color that comes from something here. I can go to definition. This is where the color is defined, control outline color. And then I get a pop-up here. I can change the color, and let's pick something that is a bit closer to what we have here. Something like this. And then this is reflected right away in the design here. And this is the rapid design philosophy that we want that you can quickly try out things, see, does it look good? Is it okay? Does it fit into this light or not? That's sort of the basic idea. So we can take this and we can also run it on the device. I need to go ahead and compile it quickly, or not so quickly, and also need to reset the device. I mean, press some magic buttons. So while this is compiling, it's taking some time to optimize. We also do. We not only do a graphical user interface for embedded devices. We also have for desktop. So I can show you. We made a little cargo front end to show that we can do this. So, it's like a little cargo front end. You can run it on the project itself, and then it'll build the project and show you the messages in there. Or you can also show like the dependencies that your project has. Or this is something I personally actually use a lot. I never know what I've ever installed in command line tools with cargo installed. So this is quite neat because you can see what it is there. And you can say, there's C bindgen. That's really old. So I'll just update that one. No? Oh, yeah, I'm not on the network. OK. It would do that otherwise in the background. So we also do desktop styling. So meanwhile, this thing has printed, and now we have our awesome German version of the printer that supports faxing. And sadly, the color here on this screen doesn't come out across, but if you came here in person, you will see that it's the color I chose. Sure. We have a few other things as well. One of the demos we also have is called a slide puzzle. This is something I personally find rather addictive because the problem with those demos is that you like to play them and see if it really works. So we also run this on the desktop, and then it comes up here, and then this is like one of those things where you have to sort the tiles in the correct order. And so the same thing here can also be run on the device again. Just another magic command line. And then let's go back here so it's visible again. After a while, it should come up. Yep, there we go. So now you can it's really funny to do this. You can play the game, the puzzle here. Like me, you can play it reverse. This is the kind of stuff you can do, and this thing doesn't cost anything, so it's super easy to just get started at home and do something meaningful, not play games of it. Yeah. What else can I show? We have also there's another third little thing I can show. This is a memory game. We have a tutorial for this, and this also runs on the Pico. This is like the memory game where you have to switch to tiles, and then finally, so this is a bike, and there's another, I think there's another bike here. Yes. This is something else. No, that was wrong. So I'll see you tomorrow when I finish this game. But you get the idea, hopefully. Yeah. That's it. Thank you. I hope you enjoyed this. Any questions? Yeah.
So thank you for the talk. It's very insightful. So since you've mentioned that it's like directly interacting with the bare metal microcontroller, like how does the architecture looks like from the time you write until it compiles and then goes down to the
how does the architecture look like?
Like how is it running actually? What's the abstraction of that it is actually running on this microcontroller?
There is no abstraction running. So there is you say that there is this is my entry function, and then this is basically what's set up as an address, and there's an interrupt vector table that says that is set up in a specific address that has, or there's a sort of a startup table and that says, okay, this is where the program should really start. And then when this thing powers up, the CPU goes ahead and starts executing instructions from that point. And that's literally the entry function that you specify. There's nothing else running before that. And that's where those crates come into play that are in the ecosystem that help you set up basic things. So when you start, there's just the processor running, and then you have to set up the oscillator for the system clock. You may have to adjust that. You have to set up the bus to talk to the screen. You have to initialize the screen. You have to do all these things, and that's a little bit of boilerplate code. Typically, this is the kind of boilerplate code you copy and paste from the examples, basically. So we don't want to duplicate that all of the time. So for this device, we've put this into a crate for ourselves so that we don't have to duplicate that. So it's just one function call.
So like since, for example, this would be a commercial use if it was like a printer or whatever. So you think that like this will be irrelevant from Slint's core implementation, for example, if you want to connect to networks, do things, whatever?
Yeah. We just want to do one thing, and we want to do it well, which is the toolkit. And we want to provide, especially for microcontrollers, provide an API, low-level API that you can then combine with your own microcontroller. It is very, very, the fragmentation in this space is insane. So people who would actually build a printer with this, they would have a board that we have never seen and we will never ever see. So we want to provide just enough of an API where they know how the hardware works and they know how to bring it up, and they can report to Slint, for example, the system time, so that we can update animations. And then they will provide a buffer where we can render into, whether it's a line-by-line buffer, like on this thing, we can only render line by line. So there's not enough RAM for an entire frame buffer, so we can only render line by line. So we can, somebody would use that and say, okay, here's the buffer you can render your lines into, and when you're done, let me know, and then I'll take care of transferring it to the screen.
Nice. Good luck.
Thanks.
Another question. I've got one short question. What's the price point of this combination with the display around when I want to start hacking today?
So the Pico is about 4 or 5 euros, and the screen is 10, 15. So overall, 20 euros, give or take.
and I allow myself to ask a second question.
Please
and
do.
that's like the display still feels a little bit sluggish, like
Yes.
slow, and it's also like resistive. I mean, capacitive is probably better. I'm just wondering, is there any hope of like getting like a really nice user experience, for instance, with like native scrolling and so on, so you get an iPhone or Android-like experience?
Definitely. So we picked this because this is sort of the lowest of the lowest, and we wanted to see how low can we basically go. This is pretty low, but for not much more money, you can get more powerful devices. And so, for example, the STM series, like what ST Microelectronics does, they have pretty reasonably priced microcontrollers that have beautiful screens, capacitive touch screens. They have 2D graphics accelerators that support scrolling or blitting of regions on the screen and these kind of things. So you can, if you want to build a better user experience, you can definitely do that. And of course, you can also just go for a regular embedded device as well if you wanted to. But in this space, you can definitely get something better. So this is just really, we wanted to see go as low. How low can we go? A couple of 100 kilobytes, but you can go much better, of course, and get a better experience, definitely.
Cool.
Another one? Anyone? Yep. I try to not to hit your head.
All right, thank you for a very interesting presentation, and also the desktop application on OS X looked quite good. And here comes my question: like on desktop environments, does Slint integrate with operating systems or like desktop environments, or not really? Like, does it adapt, for example, to like Windows or desktop environments in Linux, like GNOME, KDE, GTK, and stuff like that?
Yes. That's. I mean, we're not great at that. I would say we're not sort of really good at it. But it's definitely it's clearly our objective, and it is something where we are happy to discuss and improve it, and also receive patches. And we've also received really good patches from people who had an itch there and said, oh, look, this doesn't really good. The dark mode, light mode on macOS wasn't respected, and somebody made a patch for it, and that was really cool. So yes, definitely. Do as good as we can, also not great yet.
Okay. But still very impressive, thank you.
One more, maybe? Okay. Well, thank you for this amazing talk and for the demo. Thank you.